Look closely at this inductor coil. It's glowing, vibrating, and continuously flooded with an invisible, alternating electrical current. But if we measure the net energy it consumes over a full cycle, the reading is exactly zero. To figure out how this is possible, we need to strip away the rest of the physical world and look exclusively at a purely inductive component connected to an alternating current, or AC, voltage source. This diagram shows our physical setup, driven by the AC voltage equation, V equals V sub m times sine omega t. We know the input voltage, but to understand the circuit's behavior, we must solve for two unknowns: current, I, and power, P. Let's set up a framework to track these variables. We'll use a Cartesian coordinate system with time on the horizontal axis. By applying basic calculus to the fundamental physics of this circuit, we can mathematically prove exactly how this zero power state exists. Resolving this paradox is highly practical. It forms the foundation for how engineers design safe, large-scale power grids and the high-frequency filters inside modern electronics. Starting with Kirchhoff's loop rule, the applied voltage minus the inductor's voltage drop equals zero. We rearrange terms to isolate the differential current, dI. Integrating both sides with respect to time, the sine function becomes negative cosine, giving our initial current equation for I. But we have a minor problem. Our original voltage was a sine wave, and our new current equation is a negative cosine wave. To compare their timing directly, they need to be in the same mathematical format. Using a trigonometric identity, we transform negative cosine into a sine function, introducing a minus pi over 2 offset. Graphing the voltage wave, we overlay the current wave. Notice the delay. It crosses zero exactly a quarter cycle later. This 90-degree delay isn't a mathematical glitch. It's the direct physical consequence of the inductor actively opposing any sudden change in current flow. Evaluating the amplitude coefficient isolates the inductor's unique opposition factor. Current amplitude equals voltage amplitude divided by X sub L. We define this denominator as inductive reactance, angular frequency times inductance, measured in ohms. Reactance limits current much like standard resistance. But there is a critical distinction. Inductive reactance is strictly dependent on the frequency of the AC signal. Looking at these graphs, the relationship is linear. As the AC frequency increases on the x-axis, the inductor's opposition to the current increases proportionally. We can contrast this high-frequency behavior by evaluating the formula at a frequency of absolute zero. A frequency of zero represents direct current, or DC. Multiply inductance by zero and reactance drops to zero. An inductor presents zero resistance to steady DC flow, acting effectively as a plain short circuit. An inductor is a frequency-dependent gatekeeper. It blocks rapid electrical changes while giving steady, unchanging currents a free pass. Translating phase shifts in your head is difficult. Engineers use a geometric tool called a phasor diagram to visualize out-of-phase waves without doing complex calculus. This sets up a static XY coordinate system where voltage and current amplitudes are straight vector arrows. Geometrically, the current vector is locked precisely at a right angle behind the voltage vector. To represent time, we rotate these locked vectors counterclockwise. Tracing their height onto a time graph perfectly draws our overlapping sine waves. Watch the peaks. When voltage hits maximum, current is just crossing zero, proving the phase shift is a structural delay. We resolve our core paradox by examining power, defined as voltage multiplied by current. Stepping through the trigonometric simplification of multiplying these sine waves leads directly to our final boxed equation. The key feature is the sine 2 omega t term. This indicates that the power is oscillating at exactly twice the speed of the voltage. Plotting this double frequency power wave over our existing waves, it completes 2 full cycles for every voltage cycle. We'll focus on the green-shaded positive sections, where power is greater than zero. These notes state the physical reality. During a positive lobe, the inductor actively absorbs energy to construct its magnetic field. During unshaded negative lobes, the collapsing field pushes stored energy backward. This brings us to the ultimate resolution of the paradox. Look at the conclusion block at the bottom. Because the positive math exactly equals the negative math, The average sum of power transfer over a full cycle is mathematically zero. An inductor cycles electrical energy with perfect mathematical symmetry, constantly borrowing and returning power to the circuit so that nothing is ever truly consumed. Bringing these models together, the theoretical framework locks into place. Physically, an inductor inherently resists current changes. Mathematically, this forces current to lag voltage by exactly 90 degrees. Consequently, this specific delay forces power to oscillate perfectly, creating a zero net sum. This flow without consumption is a direct result of perfect geometric phase alignment. This exact math is why engineers use inductors to choke out high-frequency electrical noise, achieving stability without draining a system's power budget. Mastering AC circuits requires abandoning static measurements. To understand the grid, we must calculate the dynamic, interwoven dance of changing rates over time.